Everybody, welcome to a video on section 5.1. I apologize in advance. This is not going to be particularly compelling work. It's not that interesting to listen to my boring, monotonous voice over a recording like this. However, I wanted to make this as quickly as possible so that you can watch it whenever you'd like. And I'm also going to try to keep it brief because, again, it's not super compelling to watch me do this without a whiteboard, but I'll do what I can. So it makes sense not to have class on Wednesday, but I am very sad not to do it in person because this is a super interesting chapter. I'm not sure if this section in particular is super interesting, but this is the springboard to a really interesting chapter which covers statistics. So I don't know if you know this or not, but statistics is like really useful. If you think about the applications of probability, statistics is absolutely the crown jewel application of probability. Some people would even argue that like that's the entire reason to do probability altogether, although I would disagree with that. But there's a case that could be made. So why is statistics so important? I guess we should ask, right? So statistics is important because it's how you provide evidence for claims. So don't we all think that's important, providing evidence for claims people make? I think that's important. So you probably already know this, but I will tell you anyway. If you want to answer a question like this, how do you know that drug is effective? How do you know that vaccine is effective? The answer is statistics. So statistical tools answer questions like this. How do we know that you shouldn't smoke when you're pregnant? Because people didn't used to know that like 100 years ago, but we know that now for sure. And the answer is because statistics told us that. How much you design or demonstrate that a product you made to help people quit smoking actually does. How do you demonstrate that some foods contribute or help against heart disease, whatever. Cheerios, I can't remember if they still do this or not, but they used to say this, hey, buy Cheerios and we'll lower your cholesterol. So how could you prove that or not prove it? Polling data, how do you interpret that kind of information? What is that telling you? All of this stuff relies on statistics, and the punchline is statistics helps provide rigorous mathematical evidence for truth claims. So it's just, you can't really overstate the importance of statistics. Here's the outline of the chapter. Today is just notation and definitions, so no real statistics here. The next section, normal distributions. Then we move on to standard deviation, central limit theorem. This is the fundamental theorem of statistics, as you might imagine, extremely important because this theorem lets us do what's called things like hypothesis testing and confidence intervals, which gets at all these things up here. And then finally, we'll end with a pretty cute application, something called Benford's Law. This isn't like foundational to statistics or something, but it is super nice. And it's something that's commonly misunderstood in quite obnoxious ways. So that'll be a fun way to end. So that's what the chapter is about. Okay, now today we're talking about continuous random variables and probabilities of those. So to motivate what a continuous random variable is, here are two different random variables with probability questions. So x is the sum of a roll of 3 dice. I could ask you, what's the probability of getting a sum of 4? This x is the choice of a random number between 0 and 1, any real number. So 0.0385923, whatever, right? Any number like that. So this x here, if I ask you what values can it take on, well, when you roll 3 dice and you look at the sum, you could get a value of 3 or 4 or 5, 6, all the way up to 18. So the thing about those values is, first of all, there's finitely many of them, just from 3 to 18. But secondly, and this is the key point, there is space between those numbers. Like between 3 and 4, there's a bunch of space, a bunch of numbers in there. Between 4 and 5, a bunch of space. Whereas here, this x, there's no real space between the outcomes. Like the interval between 0 and 1, there's no gaps in that. So this x can take on an infinite amount of values. There are infinitely many fractions between 0 and 1. And furthermore, there's no gaps like there are between the number 3 and number 4. So this x here is qualitatively different from this one. This x here is called a discrete random variable. Discrete basically meaning there's gaps between the outcomes. So 3, 4, 5, 6, whatever, things like that. Usually discrete random variables take on integer values, although not always, whereas this x takes on real values as values, and there's no space there. There's no gaps in what x could take on. So this right here is a continuous random variable. So anyway, a random variable is said to be continuous if there's no space between its outputs. Okay, so hopefully that makes sense. By the way, if none of this does make sense, I will be in that Zoom link at 11:15 tomorrow if you want to talk to me. So feel free to show up if you have questions. Okay, so now we haven't used this language before, but everything we've done so far is with discrete random variables. So our sample spaces were finite and usually integer valued. Whereas now, that's not going to be the case. Our sample spaces will have infinite size, and there'll be no space between, no gaps in the outputs. Statistics runs on continuous random variables, as we will see. Now, discrete things are often modeled by continuous things for computational purposes, so we'll also see that also, and then we can recapture a bunch of previous results with what we'll do in Chapter 5. So that's super nice. Now, before we move on, one quick point to make is that if x is continuous, you never think about the probability of getting some exact value anymore, because like back up here, what's the probability of seeing that exact number? Well, the sample space size is infinite. Like there's infinitely many numbers between 0 and 1. So this is one value, and there's infinitely many values. So I guess you'd be writing this, which is 0. So the probability of seeing some exact number when x is continuous is just 0. So you don't even bother with these kinds of quantities anymore. Instead, we think about this. What's the probability my random variable takes on a value between, like, say, 0.1 and 0.3, or between 0.4 and 0.8, whatever. So instead of thinking about taking on a single value, we'll think about an interval of values. What's the probability x lives between a and b, as opposed to what's the probability x is a? Okay. So finally, the big definition, how do you measure probabilities? Like what I just said, probability x lives between a and b. You build a function f of x so that the area under the curve of f of x. Wow, integral. So here's Calc 1 and Calc 2 being used. That's nice. So little f of x is a function such that if you look at the area under its curve on the appropriate interval, that will tell you about the probability of the random variable under consideration. So this is, again, like kind of like an analog of the probabilities before. So our probability functions before were like scatter plots. Like if you think about rolling a single die, the probability of getting a 1, 2, 3, 5, or 6 is just a sixth, and we would draw that scatter plot sometimes. So now you don't have a scatter plot though, because your variable is continuous. So now you have like a real live Calc 1 function, and you look at areas under the curve to give you probabilities. So if that's abstract, and it is, let's look at an example. So the cholesterol level for an adult male from some racial group has this probability density function. So boom, there is a function. Now it's not a particularly nice function, but it is a function. This is something like you could write down in Calc 1. And then you could think about what's the probability that if I choose somebody at random from this racial group, their cholesterol level lives between 4 and 7. So how would you answer that? Well, by the definition. So this function, if you look at its area under the curve from 4 to 7, the resulting outcome is the probability. So, this is now a Calc 2 exercise, I guess. We're not, like, this isn't an integration techniques class, so we're not going to do any integrals by hand. So instead what you do is you take this function and ask Wolfram, what's the area under the curve from a to b? And Wolfram can do that. So integrate from wherever to wherever, that's the syntax, and then give it your function. So see this from 4 to 7, there's the probability density function, and it gives an answer of like 96%. It also gives you this nice little visual. So from 4 to 7. So this curve here, this is the probability density function. And look at all this area from 4 to 7. Look at like how little white there's left over, right? So this curve, most of its area lives between 4 and 7. That's why this fraction is so high. Okay, so anyway, there's an example for you. What's the probability a randomly chosen male has a cholesterol level between 4.8 and 6? All you do is you go back to Wolfram and do 4.8, 6. And as you might expect, the probability has gone down because we narrowed our range. So now it's showing you again, like there's a bunch of white space over here, a bunch of white space over here. So still, the majority of the area is between 4.8 and 6, but now there's 38% outside of it. So if you want to see the full picture here, here is the, let's zoom in a little bit. There's the probability density function. So 4.8 is like right here, 6 is right here. So you're filling in this area here, and there's a bunch left that's not in there. Okay, and then finally, you could ask, what's the probability that somebody has exactly this cholesterol level? And as we've discussed, you don't really care about questions like that. If you wanted to think about it, you could, but then like exactly 5.5 means a 5.5 there and there. And when you integrate from number to same number, there's no area. The area is 0. So if you go to Wolfram and you're like, oh, from 5.5 to 5.5. Wolfram says, why'd you ask me that? The answer is 0. It doesn't bother to give you a graph anymore. Okay. So that's the idea of this section. So we have variables that can take on real values now. Like this random variable, I guess, could potentially be any real number greater than or equal to 0. So you could have a cholesterol level of whatever, 4.8, 7, 3, 2, 5, whatever, right? Anyway, and so with a variable like that can take on real values, we're only looking at ranges in the domain. Okay. Oh yeah, so if we were in class, I'd force you to think about this. What if you looked at all the area under the curve? From negative infinity to infinity. What should that be? And the thing is, if this is supposed to give you probabilities when you integrate it, right? So when you integrate from someplace to someplace, it's supposed to give you a probability. Probabilities can't be bigger than 1. So at the very least, your answer here should be 1 or smaller, I guess, right? If it was 1 or bigger, it's like you're saying there's more than 100% in the system, which makes no sense. Also, though, like back in this question, if I ask you, hey, I choose somebody from this group, what's the probability their cholesterol lives between negative infinity and infinity? I mean, the answer is 1, 100%. I guarantee you this person has a cholesterol level between negative infinity and infinity. So probability density functions, basically their defining characteristic is that this integral is 1. The other defining characteristic is that f of x is always at least 0. Like it would make no sense for this curve to dip below the x-axis because that might give you negative probabilities sometimes, which makes no sense. So probability density functions live on or above the x-axis, and their total area under the curve is 1. Okay, next big definition, recall the expected value formula. That was for discrete random variables. We'll use that a ton. But now, if you can have infinitely many values and there's no gap in the data, like how do you adapt this formula? And the punchline is this. So you got to sort of mimic this. Outcome times probability plus outcome times probability. The thing about an integral is it's basically just a big old sum via a limit. So all of you at some point in Calc 1 or Calc 2 saw the definition of integral, and it's just a big old summation that you're letting run to infinity. So that's all that's happening. So look, outcome times probability. F of x is playing the role of probability now. So the expected value of x is outcome times probability. Add them all up. Add them all up from left to right. So it's like if you think about it enough, this is actually what you would be forced to write down to make any sense. If you already have this definition in hand, like you would have no choice but to do this to mimic that definition. Okay, so now let's think about the expected cholesterol level, for example, 1. So I come back up here, I integrate from negative infinity to infinity, like that, and x times. So here's little f, that's probability. Now outcome times probability, and it says 5.2. So if you take samples of people from this this group over and over and over again and measure their cholesterol, on average you'll see a cholesterol level of 5.2. And notice if I take the x times out, it tells me 1. So that's what we should see, because this is just the probability function here. So this again is saying, like, the probability your cholesterol lives between negative infinity and infinity is 1. That's all that's saying. So for the expected value, you just scale that by x inside the integral. And now you don't get a 1 as the output. You get the average cholesterol level, which is 5.2. Okay, so that's basically all the material here. We'll use this later. The book mentions it now. We've already used this in section 3.2 for discrete variables. It still holds for continuous, but this is nice to have, that the expected value function is linear. So you can split it over sums. Okay, so now here's another example. If we were in class, I would just make you do this, but you're not in class, so we'll just do it now. Okay, so the wait time x in minutes for customers to be on hold has this probability density function. So I'll show you what that looks like. And let's zoom out. Okay, and then zoom back in, like right here. That's what it looks like. So notice the area under the curve is sort of clustered around 0. And from 0 to like 5 is where all the area is. Notice there's no area over here to the left of 0. That makes sense because you can't be on hold for a negative amount of time. So if I give you this function and say, hey, what's the integral from negative 5 to negative 1? If you're integrating 0, the answer is 0. So the probability is 0 that you will be on hold for a negative amount of time. So let's think about this question, though. What's the probability you have to wait for more than 2 minutes? Okay, so more than 2 minutes. I'll come back up here, integrate. So it was 3 over x plus 1 to the 4th. 2 or more means 2 or more, like that. So like a 4% chance. This is a pretty good customer hold line, right? This is not like me trying to call Southwest Airlines over Christmas break. This is the opposite of that. Yeah, so their probability density function, you can go ahead and take this curve and drag it about 5 hours to the right, and that's what you're looking at. But anyway, I mean, 2 or more, look at how little area there is. So that's like only 3% of the area. That's what Wolfram is telling me. The rest of the area is concentrated over much farther to the left. Yeah, 4% of the area. Okay, what's the next question? Has to wait for 20 seconds or less. Okay, so now I'm getting cute. Always dangerous to use different units. So minutes, seconds. Okay. So let's see if I can handle that. So now, when you're doing Wolfram here, you don't want to put a negative infinity here, because Wolfram doesn't know that you're doing a piecewise thing. It doesn't know that you actually want this to output 0 to the left of 0. So call time, wait time start at 0, and then 20 seconds. What's that, a third of a minute? Like that. So about 58% of the data is clustered, here. I mean, look at all that area, right? So they answer their phones pretty quickly. So again, I just want to belabor the point here that if you think to yourself, oh, 20 seconds or less. So I'll just come in here and be like, 20 seconds is there or less. It says, oh, I can't do that. It says infinity is what it's saying. It's a divergent integral. So you then don't want to write on your paper, oh, the probability is infinity, right? Because that makes no sense. Probabilities are at most 1. So again, the error is this function doesn't come online until time 0, like that. And Wolfram doesn't know that you were dealing with something piecewise here. Okay, what is the expected wait time? Okay, so now, again, we have to be careful. The expected value is x times f of x, from negative infinity to infinity. But again, you can't just blithely do that. So again, let me show you this. X times from negative infinity to infinity. If you try to just kind of blindly follow that formula, it's going to again tell you infinite, which makes no sense. Like, you're telling me on average I have to wait an infinite amount of time. That's what does not converge mean. And no, that makes no sense. We saw the picture. It looks like they answer their phone super quickly. So no, it shouldn't take on average an infinite amount of wait time. So the error here again is like this function is not coming online until x equals 0. So to the left of 0, like what you're actually integrating, you're integrating the function 0. You're integrating the function 0 to the left of 0. And then you're integrating this to the right of 0. Now the integral of 0 is 0. So the only part of the definition that survives is this piece. And there you go. So on average, you wait half of a minute. Okay, so at the end of this, hopefully, we have an understanding of continuous random variables, like what that means. Hopefully we understand how to calculate probabilities for them, given a range, like between something and something, get the probability, and we have an understanding of the expected value. So expected cholesterol level, expected wait time. That's the point of this section. Now notice we didn't do any of this stuff, did we? All these interesting questions. So we get to that later. And when I say later, I mean here. So we have some machinery to build before we can answer the interesting questions. Okay, make sure that if any of this doesn't make any sense, you let me know. Hopefully I will see you on Friday.